All right, good afternoon, everybody. Hope everybody's doing well. We'll pick up from where we left off last night in a moment. And again, if you have any questions or anything, you can use the chat feature, which I have available and open. And you could also use jump in if you want to jump in as well. So either way would be acceptable. All right. So we finished last night by looking at the reactions of esters. So today we pick up by looking at the reactions of amines. Now, when we had our discussion of carboxylic acids, we talked about the fact that carboxylic acids behave as acids, not only according to the Arrhenius definition, but according to the Bronsted-Lowry definition as well. And the two reactions of carboxylic acids that we took a look at were dissociation in water, Arrhenius, combination of Arrhenius and Bronsted-Lowry in terms of what it does in water, and then its neutralization. Well, remember, amines are derivatives of ammonia. Now, remember, ammonia has the chemical formula of NH3. And essentially what we do for amines is we take out one or more of the hydrogens of ammonia and we replace them with carbon groups. Now, ammonia is a weak base. And remember, for weak bases, there really sort of is no Arrhenius definition of a weak base. Weak bases sort of tend to only be poor acceptors of protons from water. Well, because amines are derivatives of ammonia, they sort of tend to have the same properties of ammonia. And we'll start by looking at their first reaction, which is their behavior in water. So essentially, when you take an amine and you place it in water, it's going to behave as a weak base. We can look at this as sort of first with a general equation for this process. So you have your amine where the nitrogen is going to have 3 bonds, and we're going to react that with water. Now, because it's a weak base, we're going to have a double arrow. And essentially, when we talk about the nitrogen being a weak base and we focus on the Bronsted-Lowry definition, we talk about nitrogen being a proton acceptor. Not a very good one, but we're talking about the nitrogen being a proton acceptor. Where does the proton come from? The proton comes from water. So the other product for this reaction is going to be OH minus. Like I mentioned the notes, and as I talked about last night as well, when you have multiple products and one of them is not organic, you're not responsible for that product. I would give that product to you, and you'll see this in the examples we work on again today. But the other product of this reaction would be OH minus. So just like ammonia produces solutions in water produces a solution in water that is weakly basic, your amines will produce solutions in water that are weakly basic as well, because they tend to generate OH minus just like ammonia does when you place it in water. Now, specifically, what happens to the amine? Well, everything stays the same, but the nitrogen is going to pick up a hydrogen. Now, when nitrogen has 3 bonds, the nitrogen is neutral. But when nitrogen has 4 bonds, the nitrogen has a positive charge. So it's going to have 3 things already attached to it. It could be carbon groups, it could be hydrogen, depending on the structure of the amine. But when the nitrogen picks up the hydrogen, it goes to 4 bonds. So the nitrogen starts out as being neutral, but then in water, when it picks up the proton, it now has 4 bonds and a positive charge. Okay. Let's look at one or two specific examples. And I'm just going to go vertically to give myself some more room. All right. So here is the first example. Let's see if we can make it just a little bit clearer. All right. So we have the following amine, which, just for a point of discussion, this is a primary amine. And remember, the way we classify amines is the number of carbons directly connected to the nitrogen. So this nitrogen has one carbon directly connected to it. So it would be classified as a primary amine. To solve this problem, that really doesn't come into play, so to speak, but just as sort of a point of reference, need to be able to classify amines as well. So you have an amine, you have water. What are you going to have to remember? You're going to have to remember that the amine is going to behave as a Bronsted-Lowry base. The nitrogen of the amine is going to behave as a proton acceptor. So it's going to pick up a hydrogen from water, and that's why the water becomes OH minus. So to draw the structure of the main product, everything is going to stay the same until I get to the nitrogen. Now, in this case, when the nitrogen picks up a hydrogen, the nitrogen goes from having two hydrogens to now having how many hydrogens total? 3. So we could write that as NH3. The nitrogen had 2 hydrogens. When it picks up one more hydrogen, it now has 3 hydrogens. But in total, the nitrogen has 1, 2, 3, 4 bonds. So what charge is the nitrogen going to have? The nitrogen is going to have a positive charge. And that is the structure that would form in this example here. All right. So that's how this amine would behave in water. Let's do one more example. All right, let's consider the following amine and its reaction in water. Oh, that's okay, no worries. I'm recording it, so I'll post it to Canvas as soon as we're done. No worries, I understand. All right, so what type of amine do we have here? Here we have a secondary amine. And the way that we know that is the nitrogen has 1, 2 carbons directly attached to it. Sorry about that. Why is it not working? Let's see what we can do. Okay, hopefully this will work. All right, so the nitrogen has 2 carbons attached to it, just making it a secondary amine. So again, amine, water, what do we have to remember? We have to remember about its behavior as a Bronsted-Lowry base, a proton acceptor. So when I draw the product, everything's going to stay the same until I get to the nitrogen. Now, the nitrogen already has a hydrogen attached to it. It's going to pick up a hydrogen, so it goes from 1 hydrogen to now having 2. So instead of writing NH, we could write NH2. But then also don't forget the nitrogen is still connected to the ring on the right. So at the end of the day, the nitrogen has how many bonds total? 1, 2, 3, 4. So again, the nitrogen is going to have what charge? The nitrogen is going to have a positive charge associated with it. Okay, and that is the structure of the product that would result here.
Can you just show the bonds again on the nitrogen?
Sure. It would have, and I'll draw it out a little bit further. So you'd have the ring, the nitrogen, and then it's got two hydrogens attached, and then it has the other ring. So you have 1, 2, 3, 4. So if you see NH2, that means the nitrogen is attached to two hydrogens. So that's 2 bonds. Here's the third, and then here's the fourth. So those would be the 4 bonds total.
Thank you.
And if you're more comfortable drawing the bonds out, absolutely draw the bonds out. Even the original structure, you see it as NH, but if you wanted to sort of draw that out and make the hydrogen expanded, you can definitely do that as well. So, if you're not so comfortable with the condensed forms where the hydrogens are sort of grouped with carbon or nitrogen, then definitely take the time to draw those out. All right, so that's the first reaction that amines undergo. The other reaction that amines undergo is neutralization. Now, we saw an example of neutralization when we talked about carboxylic acids. And remember, neutralization is the reaction of an acid and a base to give a salt and water. For carboxylic acids, we talked about the fact that a carboxylic acid will react with sodium hydroxide or potassium hydroxide to give you water and a salt, generally known as a carboxylic acid salt. Here, you're talking about the reaction of an amine with an acid. And specifically, the acid that's used by the textbook is HCl. And then, of course, they put in the homework about using HBr. But in essence, whether you use HCl or HBr, it's basically the same thing. Remember, chlorine and bromine are in the same group in the periodic table. So HCl and HBr are very similar to each other. What makes this neutralization different from most neutralizations that you come across is that here, we're going to get a salt, what is known as an amine salt, but what we're not going to get is water. Remember, the general idea of neutralization is acid plus base gives you salt and water. Here, when an amine undergoes neutralization, you're going to get a salt, but what you're not going to get is the water. And the type of salt that you're going to get is what is known as an amine salt. All right. So let's look at a couple of examples. Since we can use HCl or HBr, instead of sort of focusing on a general equation, and I would tend to focus mostly on HCl because that's sort of what the textbook does, and then they throw a curveball in the homework by doing HBr. I'll show you an example of both, but we'll sort of just stay away from the general equation in this particular instance. So let's take a look at first example. Now let's go back to the amine. One of the amines that we used on the previous slide. Okay. So you have your amine, you have hydrochloric acid. The reaction is going to be neutralization. How do you come up with the amine salt? Well, first off, the HCl. So we talked last night a couple different times that when you have sodium or potassium hydroxide in a reaction, we don't tend to think of it as NaOH or KOH because as strong bases, and we think about using aqueous solutions of those substances, we know that their dissociation in water is going to be complete. So when you look back on what we talked about for reactions that involved using NaOH or KOH as a reactant, we talked about using the NaOH or thinking about the NaOH as Na plus and OH minus. And we talked about thinking about the KOH as K plus and OH minus. HCl, as we know, is a strong acid. So we're not going to think about it in this case as HCl. We're going to think about it as H plus and Cl minus. The nitrogen in the amine, which even though we don't show it a lot of times, has a lone pair of electrons. Essentially, that nitrogen is going to pick up the proton that's generated from the acid. Whether it's HCl or HBr, because HBr is a strong acid as well, the nitrogen is going to behave still in these reactions as a Bronsted-Lowry base. It's going to behave as a proton acceptor. Where is the proton going to come from? It's going to come from the acid. So when I draw the product here, everything stays the same until I get to the nitrogen. Now, again, the nitrogen started out with 2 hydrogens. When it picks up a proton from the acid, the nitrogen now has 3 hydrogens total. It has 3 hydrogens total. How many bonds does it have total? It has 4. Hydrogen, 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 3 separate hydrogens, and the bond to this carbon right here. So that's 4 bonds total. And of course, when nitrogen has 4 bonds, what charge does it have? It has a positive charge. Now, what else is present in this reaction that's going to be attracted to that nitrogen with the positive charge? It's going to be the Cl minus. What type of bond do you have between the N plus and the Cl minus? You have an ionic bond. And as I talked about last night, when we generated carboxylic acid salts, which had C double bond O, O minus, and then Na plus, or C double bond O, O minus, and K plus, we do not draw a dash or a line between the O minus or Na plus or the O minus and the K plus, because the bond that holds them together is an ionic bond. Here, we do not draw a dash between the nitrogen and the chlorine, because if we do, it's actually incorrect. In organic structures, how do we indicate that ionic bonds are present? We show the charges that are present. The nitrogen with the positive charge, the chlorine with the negative charge. The nitrogen and the chlorine are going to be attracted to each other by an ionic bond. And remember, your salts are sort of recognized by having ionic bonds. What type of salt is this? This is an example of what is known as an amine salt. So this is the amine salt that would be generated here. And notice, no water being generated from the process. No water being generated from the process. Let's look at one more example. And let's look at HBr in this case. So let's use the amine, the other amine we did on the previous slide. Okay. So we have our amine, we have HBr, okay? So the reaction of an amine plus HBr, HCl is going to be neutralization. We're going to get the formation of an amine salt. Now again, HBr, just like HCl, is a strong acid. So we're not going to think about the HBr as HBr. We're going to think about it as H plus and Br minus. Its dissociation is going to be complete. just like HCl's dissociation would be complete. The nitrogen, again, is going to pick up the proton from the acid. So when I start to draw my main product, my salt, when I get to the nitrogen, again, the nitrogen goes from having one hydrogen to now having how many? 2. So we can write that as NH2. And then don't forget the nitrogen is still attached to the other ring on the right side. The nitrogen therefore goes from having 3 bonds to now having 4 bonds total. When nitrogen has 4 bonds total, what charge does the nitrogen have? It has a positive charge. What else is present in this reaction here that's going to be attracted to that N plus? You're going to have Br minus. And what you don't want to do is you don't want to squeeze the Br minus into the middle of the structure here, because you don't want to imply at all that the nitrogen or that the bromine, the Br minus, is covalently bonded to anything. So just really put it out of the way. Put it to the right, put it to the left, put it to the top. But the one thing you don't want to do is you don't want to try to squeeze it in between the nitrogen and those covalent bonds. I think in the homework, I'm seeing a little bit of that. You don't want to try to squeeze it in between. So you don't want to imply at all that the Br minus is covalently bonded to anything. Just put it to the outside. If the nitrogen is in the middle of the compound, just put the Cl minus or the Br minus to the outside. And, this way, with the charges that are present, we would recognize that there's an ionic bond between the nitrogen and the bromine. All right. So neutralization is the other reaction that amines undergo. Okay. You could do plus Br minus, but in reality, this would be one substance. The NH2 plus and the Br minus would the cation, so to speak, the structure here, and the anion would really be one substance. So you don't have to put in the plus Br minus. I know in the other reactions we put I don't know why I'm not able to go back so much. With the other reactions, we're not able so much to, or I'm sorry, we put plus OH minus. If you left out the plus OH minus, I guess that would be okay as well. I don't know if you'd have so much of an attraction between the N plus and the OH minus. You would definitely have more of an attraction between the N plus and the Br minus. But if you wrote plus Br minus, technically it wouldn't be wrong, but you really would get a singular product for this example here. But the best thing I would say to do is to just essentially leave this as is. That would be perfect. Okay. So the last functional group that we come across in chapter 14 are your amides. So for an amide, we have a carbonyl group, a C double bond O group. But what defines an amide as an amide is that the C double bond O carbon is going to be connected to a nitrogen. So for amines, essentially, the nitrogen is attached to either hydrogens or essentially hydrocarbon groups. Usually alkyl could have a benzene ring attached to it as well. But for an amide, one of the things that nitrogen is going to be attached to is a carbonyl group, a C double bond O group. So the way we sort of look at it is that when you have C double bond O connected to nitrogen, that gives you what is known as an amide. As you saw in the notes, the different types of amides come from what else is attached to the nitrogen. If there's 2 hydrogens, it's a primary amide. If it's a hydrogen and a carbon group, it's a secondary amide. And if there are 2 carbon groups, it's a tertiary amide. So you should be able to recognize the different types of amides. One of the things to sort of keep in mind is that for amines, the nitrogen can definitely have 4 bonds attached to it. We saw that in these examples. There's really no issue with the nitrogen having 4 bonds for an amine. In that case, it would be a salt rather than a typical amine. Remember, amines, the typical amines are primary, secondary, tertiary. Remember the quaternary ones, the ones that have 4 bonds, 4 carbons attached for truly quaternary, but the ones that have 4 bonds total are really a class unto themselves because they're ionic. The nitrogen in an amide, for reasons which we won't get into, but the nitrogen in an amide can never have 4 bonds. It's always going to have 3 bonds associated with it. So the first reaction is one of the ways to make amides. And it is from a carboxylic acid and either ammonia, a primary amine, or a secondary amine. Now, if you think about it, and you'll see this in our discussions today, the chemistry of amides, especially their reactions, are very similar to that of esters. When we talked about esters, one of the main ways to make esters was by esterification, the reaction of a carboxylic acid with an alcohol under acidic conditions. The main way to make an amide is by the reaction of a carboxylic acid with either ammonia, a primary amine, or a secondary amine. The one type of amine that cannot be used to make an amide is a tertiary amine. And after we go through the general equation in a moment, I think it'll be very clear why a tertiary amine cannot be used. All right, so let's take a look at the general equation. Okay, so you've got your carboxylic acid, you've got either your ammonia, your primary amine, or your secondary amine. And the requirement that the nitrogen has to have is that it's got to have a hydrogen attached to it. That's why your tertiary amines cannot be used. Because if you think about a tertiary amine, the 3 things attached to the nitrogen are all carbon groups. The nitrogen doesn't have a hydrogen. In order for the amide to form, the ammonia or the amine, ammonia is going to have hydrogens. The amine, the nitrogen, has to have a hydrogen. The byproduct of the reaction is water. Again, you're not responsible for the water. We would give that to you. How do we come up with the water? Well, first off, we go to the carboxylic acid, and from the carboxylic acid, we take off the OH. Then we go to the ammonia or the amine, and from the nitrogen, we take off the hydrogen. The OH and the H combine to give you water. The bond formation that you get is a bond between the C double bond O carbon of the carboxylic acid to the nitrogen of the amine. That's the connection. These 2 pieces are going to come together where you're going to have a bond between the C double bond O carbon of the carboxylic acid to the nitrogen of the ammonia or the amine. When I draw the product, and you'll see this as we do some examples in a moment, I like to start with the carboxylic acid portion first. Everything stays the same until I get to the C double bond O carbon. And from there, now I have my connectivity to the nitrogen of the ammonia or the amine. And when one of those hydrogens, or if the hydrogen or one of the hydrogens comes off the nitrogen is still going to have 2 other bonds attached to it. And what type of structure do we end up with? We end up with an amide. And notice that the nitrogen started with 3 bonds. It's still going to end up with 3 bonds. Because again, in an amide, the nitrogen cannot have more than 3 bonds. So that's the general equation. Go to the carboxylic acid, take off the OH. Go to the ammonia or the amine, take a hydrogen off the nitrogen, and link them together by bonding the C double bond O carbon of the carboxylic acid to the nitrogen of the ammonia or the amine. All right, let's look at some examples. All right, so here's the first. So we have a 3-carbon ring, and attached to the top carbon, we have a CH2 connected to C double bond O, connected to OH. And then we're going to react that with ammonia, NH3. So carboxylic acid plus ammonia, what product am I going to have to draw? I'm going to have to draw an amide. How do I come up with that? First off, let's go to the carboxylic acid. And from the carboxylic acid, let's take off the OH. Then we'll go to the nitrogen of ammonia. And from the nitrogen, we'll take off a hydrogen. The OH and the H combine to give you water. The bond formation that you get is a bond between the C double bond O carbon of the carboxylic acid to the nitrogen of the ammonia. That's how we're going to put the two pieces together. When I draw the product, I'll start by drawing the carboxylic acid portion first, and everything stays the same until I get to the C double bond O carbon of the carboxylic acid. It's at that point where I have my transition from the carboxylic acid to the ammonia or the amine. In this case, to the ammonia. So the C double bond O carbon is going to be attached to the nitrogen of the ammonia. And when I take off one of the hydrogens from the ammonia, how many hydrogens are still attached to the nitrogen? There's 2. So we could write that as NH2. And that's the structure of the amide that would form here. So that's one example. Okay. Let's take a look at one more example. Let's just take a look at the example here. So here we have a carboxylic acid. In this case, we're using a secondary amine. Again, the nitrogen has 2 carbon groups attached to it, so the amine is secondary. That's fine. Carboxylic acid plus secondary amine. What type of product are we going to get? We're going to get an amide. How do we come up with it? First off, let's go to the carboxylic acid. And from the carboxylic acid, let's take off the OH. Then let's go to the nitrogen of the amine. And from the nitrogen, we're going to take off the hydrogen. The OH and the H combine to give you water. The bond formation that you get is a bond between the C double bond O carbon of the carboxylic acid to the nitrogen of the amine. To draw the amide, I'm going to start with the carboxylic acid portion first. Everything stays the same until I get to the C double bond O carbon of the carboxylic acid. And once I get to there, now I have my transition from the carboxylic acid into this case, the amine. So I have my bond between the C double bond O carbon and the nitrogen. Now, when the hydrogen comes off the nitrogen, what are the 2 things that are still attached to the nitrogen? They're both CH3s. The trick is just to put them separately attached to the nitrogen, because they're not connected to each other. They're separately connected to the nitrogen. So I'll draw one going down. And the other to the right. if you wanted to draw one to the top and the other to the bottom, that would be perfectly fine. The common mistake I would see in this example from students is they would put the CH3s, sort of connected to each other. That's not the case. The CH3s are separately connected to the nitrogen. So you can sort of fill them in however you want, just make sure that they are separately connected to the nitrogen. And that's the amide that would result here. All right, so that's the main way that amides are made, from the reaction of a carboxylic acid with either ammonia, a primary amine, or a secondary.
How come the nitrogen didn't get a hydrogen from the?
Because essentially, in order to get water, we take the hydrogen off the nitrogen and the OH from the carboxylic acid. So that gives you your water. So in order for the nitrogen to become bonded to here, it's got to lose something, because the nitrogen in an amide, the nitrogen is only going to have 3 bonds total. What it's going to give up is it's going to give up a hydrogen. So that's why here it still has the CH3s attached to it, but now it also has a bond to the C double bond O carbon. It can't still have that hydrogen, because then the nitrogen would have 4 bonds, and in an amide, a nitrogen can never have 4 bonds. That's why the one type of amide that doesn't work is tertiary, because if you had a one type of amine that doesn't work is tertiary, because if you had a tertiary amine, like let's say you had trimethylamine, this cannot be used to make an amide, because when you go to take off a hydrogen, there's none there to remove. And for an amide, the nitrogen can only have 3 bonds. It can't have 4 bonds attached to it. All right. So that's the one reaction that, that's the first reaction for our discussion of amides. All right. The other reaction that amides undergo, so this is now amides themselves, is hydrolysis. And if you remember back to the discussion of esters, we talked about hydrolysis, the splitting apart of an ester in water under both acidic and basic conditions. Well, it turns out that amides can be split apart upon reaction with water under both acidic and basic conditions. So as we did in the notes, and as we'll do here, we'll talk about the 2 different types of hydrolysis separately. All right, so let's start with acid hydrolysis first. So here, the products are a carboxylic acid and either an ammonium salt or an amine salt. So you get a carboxylic acid, and the nitrogen part is going to become a salt. The process in terms of drawing the salt is going to be the same in terms of whether it's a primary amide, a secondary amide, or a tertiary amide. But the difference in the different types of amides and their hydrolysis is the type of salt. If you use a primary amide, the nitrogen product is going to be an ammonium salt. Specifically for our reactions, it's going to be ammonium chloride. If you use a secondary or a tertiary amide, the type of salt you're going to get for the nitrogen part is going to be an amine salt. But independent of the type of amide, how we're going to draw the products, the carboxylic acid and the salt, are going to be the same. So with that being said, let's take a look at a general equation. Oh, sorry. Let's not fill in hydrogens there since we're being general. So we'll have our amide, we'll have water, and the acid that the textbook uses and will follow along is hydrochloric acid, HCl. So we'll have our amide, we'll have water, we'll have acid. That's how you're going to recognize acid hydrolysis. Couple things before we begin. When we talked about esters, and we talked about the key bond for an ester, where it was the bond that forms when esters are made, and that was the bond that broke when esters split apart. And we identified that key bond as the single bond between the C double bond O carbon and the what I call the alcohol oxygen. For amides, I would say that there's a key bond as well. And that key bond is the bond between the C double bond O carbon and the nitrogen. As you saw in the as we just did, that is the bond that results when amides are made. And as we'll talk about now, that's the bond that breaks when amides split apart. You know, for esters, we had to identify the carboxylic acid portion and the alcohol portion. For amides, we should be able to identify the carboxylic acid portion and what I'll call the nitrogen portion. But I just think it's a little bit easier because the C double bond O part and whatever else is attached to the C double bond O carbon has to be the carboxylic acid portion. And then the nitrogen part, of course, has to be the nitrogen portion. The other thing is, just like we did a few minutes ago, when we talked about HCl, and not thinking about it as HCl, but thinking about it as H plus and Cl minus, we're going to do the same thing here. We're going to think about the HCl as H plus and Cl minus. Strong base, sorry, strong acid and water, dissociation is going to be complete. Okay. The nitrogen is going to pick up two hydrogens, one from the water and the other, the proton from the acid. So the nitrogen is going to have two things attached to it, and that goes back to the original structure of the amide itself, which would be the bond here and the bond here. But then the nitrogen is also going to pick up two hydrogens. Now, depending on what else is attached to, it might have even more hydrogens than that, but essentially the nitrogen is going to pick up two hydrogens. The nitrogen goes to now having how many bonds total? 4. So the nitrogen has what charge? Positive. What else is present in this reaction that's going to be attracted to that N plus? It's going to be the Cl minus. And again, notice how I put the Cl minus out of the way. Because again, what type of bond do you have between the N plus and the Cl minus? You have an ionic bond. What type of substance is this? This is your salt. And again, depending on what else is attached to the nitrogen, it could be an ammonium salt or it could be an amine salt. But in either case, the nitrogen part's going to become a salt.
Is the Cl just floating?
Essentially, you can look at it as sort of floating. It's going to be close to the N plus, somewhere close to it. But again, we just don't want to put it near any of the covalent bonds because we don't want to imply that it's covalently bonded to anything. So that's why we just sort of say, put it out of the way. And when we see the charges, we recognize that there's an ionic bond between the N plus and the Cl minus. But I guess if you want to look at it as sort of floating, you can sort of look at it that way as well. Okay. The C double bond O carbon is going to pick up the OH from the water. So what does that lead us to? That leads us to our carboxylic acid. So you get your salt, and you also get your carboxylic acid. Those are the two products of amide acid hydrolysis. All right, let's look at a couple of examples. Let's see. Okay, here's our first example. So we have an amide, we have water, we have acid. What reaction is going to take place? Acid hydrolysis. First off, where's the amide split apart? Splits apart between the C double bond O carbon and the nitrogen. The other thing we'll remember is that we won't think of the HCl as HCl. We'll think about it as H plus and Cl minus. Okay. The nitrogen is going to pick up two hydrogens, one from the water, the other, the proton, from the acid. So the nitrogen started out with two hydrogens. It's going to pick up two more hydrogens. So it's going to have four hydrogens total attached to it, which we could sort of write out condensed as NH4. So it had two hydrogens, it picked up two hydrogens, now it has four hydrogens total, so now we have NH4. When nitrogen has four bonds, it has a positive charge. What else is present in this reaction that's going to be attracted to that nitrogen? We're going to have Cl minus. What type of salt is this? This is an ammonium salt because NH4 plus is what is known as the ammonium ion. So this is an ammonium salt, specifically, and you don't have to know this, but this would be ammonium chloride. So this is the nitrogen salt that would form here. If you wanted to draw out the bonds between the nitrogen and the four hydrogens, absolutely feel free to do so. But you could also write it in this case as NH4. The C double bond O carbon is going to pick up the OH from the water. And I probably should have circled that instead of boxing it. And of course, sort of boo-boo. So let's see if we can undo that. All right, let me go back and redraw. Let me see if I can just undo it. Let's see. Yeah, we sort of lost that one. No problem. Let's go back and draw that one. All right, so we had our example. We had here we had CH2, CH2, C double bond O, and H2 plus HOH plus HCl splits here. HCl is H plus and Cl minus. We talked about the NH4 with the positive charge. The nitrogen picks up hydrogen and hydrogen. Cl minus. All right. The C double bond O carbon picks up the OH from water. So for the carboxylic acid product, I have my ring connected to CH2, connected to CH2. Then I have C double bond O connected to OH. That is the carboxylic acid product that would result here. So those are the two products in this example of amide acid hydrolysis. All right. Let's do one more. Let's do. All right, let's do this one here. So again, we have our amide, we have water, we have acid. What reaction is going to take place? Amide acid hydrolysis. So again, first off, where's the amide going to split apart? Between the C double bond O carbon and the nitrogen. And then again, HCl, we're not going to think about it as HCl. We're going to think about it as H plus and Cl minus. All right. So the nitrogen is going to pick up two hydrogens, one from the water and the other, the proton from the acid. So for the nitrogen product, it has one hydrogen attached to it. It picks up two more, so it ends up having three hydrogens total, which I could write out as NH3. But then also the nitrogen is still connected to CH2, which is connected to CH2, which is connected to CH3. The nitrogen still has that carbon chain attached to it, so we can't forget about that. The nitrogen now has 4 bonds, so the nitrogen has a positive charge. What else is present that's going to be attracted to it? The Cl minus. And again, I just put it underneath to get it out of the way of everything else, to make sure that I'm not implying that it's covalently bonded to anything. So if you wanted to put it to the top, all the way to the right, to the left, is perfectly fine. Again, just do not try to squeeze it in to make it look like it's bonded to anything covalently. And then the C double bond O carbon is going to pick up the OH from water. So to draw the carboxylic acid portion, I still have my ring. And then I have C double bond O connected to OH. That is the carboxylic acid that would form here. All right. So that's amides and their acid hydrolysis. Okay. All right. In terms of base hydrolysis, so here we're looking at the reaction with essentially sodium hydroxide solution or potassium hydroxide solution, which has water present, to give a carboxylic acid salt and either ammonia or an amine. So essentially in this case, the two products are going to be different from what we saw in acid hydrolysis. As we just saw, the acid hydrolysis products are carboxylic acid and either an ammonium or an amine salt. Here it's sort of like flip-flops. Now you get a carboxylic acid salt, and the other product is either going to be ammonia or an amine. Now, when we talked about esters and their base hydrolysis, we talked about the fact that initially the reaction generates a carboxylic acid, where we talked about how the OH group of the base takes the place of the alcohol part of the ester. But then we talked about the fact that the carboxylic acid that initially forms was not one of the final products. Why? Because based on acid-base chemistry, you can have an acid under basic conditions. What happens to a carboxylic acid under basic conditions? You get a carboxylic acid salt. Very similar thing here. The reaction initially produces a carboxylic acid. And like I did in the notes, and like I will do here as well, because I do recommend it, we will draw the carboxylic acid that initially forms. But again, why isn't the carboxylic acid one of the final products here? Because we're going to be under basic conditions. In ester-base hydrolysis, first off, what's the acidic part of a carboxylic acid? It's the hydrogen of the carboxyl group. That's the part that's going to be lost under basic conditions. We saw for ester-base hydrolysis that oxygen, that hydrogen, was picked up by the alcohol oxygen. In these reactions, essentially that hydrogen is going to be picked up by the nitrogen of the amide. Okay. So again, it's kind of tricky to show a general equation for this reaction. So let's just do a couple of examples, one with sodium hydroxide and the other with potassium hydroxide. So let's use this amide first. Okay, so we have a ring. And attached to the top ring carbon, we have a bond to CH2, CH2, C double bond O, NH2. And here we're going to be using sodium hydroxide. So again, first off, where does the amide split apart? The amide splits apart between the C double bond O carbon and the nitrogen. And just like we've done previously with sodium hydroxide in reactions, we're not going to think about the sodium hydroxide as sodium hydroxide. We're going to think about it as Na plus and OH minus. Okay. Going to do some side work first. And I'll do this in brackets because initially what happens? Initially what happens is that the OH group, of the base takes the place of the nitrogen part of the amide. Okay. So the OH group of the base takes the place of the nitrogen part of the amide. So the nitrogen part's going to come out, and we're going to replace it with the OH group of the base. So if you think about it, and we draw it, now the C double bond O is going to be connected to OH. What type of compound is that? That, of course, is a carboxylic acid. So that's how we're going to get our initial carboxylic acid. But again, we're under basic conditions. So you can't have a carboxylic acid under basic conditions. What part of the carboxylic acid is lost under basic conditions? The hydrogen of the carboxyl group. In these reactions, that hydrogen is going to be picked up by the nitrogen of the amide. So in this case, that nitrogen goes from having 2 hydrogens to now having 3. So the nitrogen product in this reaction is going to be NH3. And of course, NH3 is what substance? NH3 is ammonia. So that's the first product of the reaction. Now, what happens to the carboxylic acid? Everything stays the same. So I have my ring, CH2, CH2, until I get to the carboxyl group. I still have my C double bond O, but now the C double bond O carbon is not going to be connected to OH. Instead, The C double bond O carbon is going to be connected to what? O minus. Remember, under basic conditions, the carboxylic acid becomes the carboxylate ion. C double bond O connected to O minus. What else is present in this reaction that's going to be attracted to that O minus? We have the Na plus. And what type of substance is this? This, of course, is a carboxylic acid salt. And notice how, again, I didn't draw a dash between the O minus and the Na plus, because what type of bond do you have between them? You have an ionic bond between them. So those would be the two products in this particular reaction here. All right, let's do one more example. But this time, let's use KOH as the base. So again, we have our amide, potassium hydroxide. What reaction is going to take place? Base hydrolysis. So again, where's the amide going to split apart? The bond between the C double bond O carbon and the nitrogen. Again, we won't think about KOH as KOH. We'll think about it as K plus and OH minus. All right, some side work. Initially, the OH group of the base is going to take the place of the nitrogen part of the amide. So the nitrogen part's going to come off, and that C double bond O carbon is now going to be connected to OH. And again, what type of compound is that? That is a carboxylic acid. Again, the carboxylic acid is not one of the final products here because we're under basic conditions. What part of a carboxylic acid is lost under basic conditions? It's the hydrogen of the carboxyl group. As we talked about in these reactions, the nitrogen of the amide is going to pick up that hydrogen from the carboxyl group. So here, the nitrogen product, the nitrogen has one hydrogen, it picks up another one, so now it has two, and then the nitrogen still has that carbon chain attached to it. CH2, CH2, CH3. What type of compound is that? That's an amine. So we get an amine as the nitrogen product here. What happens to the carboxylic acid? Everything stays the same, but now instead of having the C double bond O connected to OH, instead the C double bond O carbon is going to be connected to O minus. And what else is present that's going to be attracted to that O minus charge? K plus. That's the carboxylic acid salt that would form here. And again, notice that I didn't draw a dash between the O minus and the K plus because they are ionically bonded to each other. So those are the two products here. All right. So that's amide base hydrolysis. All right. So the other thing I wanted to spend a little bit of time talking about today was it comes up a couple of different times in chapters 12 and 14. Has to do with solubility in water. And the key question of what it comes down to tell whether an organic compound is going to dissolve in water is the following. Can the compound hydrogen bond with water? Because if the answer is yes, small versions of that compound, and when we talk about small versions, generally speaking, we talk about what I sort of call the 1 to 4 carbon rule. Small versions of that compound will dissolve, will be soluble in water. Now, again, what is hydrogen bonding? Hydrogen bonding is the force of attraction between a polarized hydrogen, essentially one that has a partial positive charge in one molecule. It's the force of attraction between a polarized hydrogen in one molecule and a polarized, essentially, oxygen or nitrogen in another molecule, where those atoms have partial negative charges. We'll talk a little bit about that in a moment. Essentially, if the answer is no, if the compound can't hydrogen bond with water, then the substance will basically not dissolve in water. Now, the other thing to keep in mind is that as compounds get larger, hydrogen bonding with water becomes more difficult to occur. And this essentially be for essentially types of compounds that could hydrogen bond with water. So what do I mean by that? Carboxylic acids, alcohols, aldehydes, ketones. We'll touch upon those briefly today as well. Those types of compounds should be able to hydrogen bond with water. However, what's the issue? You have to think about when you have something trying to dissolve in water, you have millions of molecules of that substance trying to dissolve with millions of molecules of water. The water molecules have to get close to specific regions of each molecule in order to be able to hydrogen bond with that type of compound. Like for an alcohol, the water molecules have to get closest to the OH portion of the alcohol in order to hydrogen bond with it. The larger and larger the carbon chains present, the more crowded the situation gets, and the more difficult it becomes for water to get close enough to where it needs to in order for hydrogen bonding to occur. If you have a compound that has one carbon, water molecules are going to get very easy, or should have easy access to the portion where it needs to get to in order for hydrogen bonding to occur. If you have a compound that has 8 carbons and let's say 18 or 20 hydrogens, or 16 or 18 hydrogens, not 18 or 20, 16 or 18 hydrogens, it's going to be more difficult for hydrogen bonding for the water to get to that sort of spot it needs to in order for hydrogen bonding to occur. Now, again, as I talked about in the notes, we're not going to expect you to know exact cutoffs. But if I give you like an alcohol, an aldehyde, a ketone, a carboxylic acid that has 9 or 10 carbons, I do expect you to know that that compound is going to be insoluble in water, because the hydrogen bonding that should occur or that can occur won't occur because of the number of carbons that are present. All right. So when you think about the different types of compounds that we saw in chapters 12 and 14. There are three types of polar sort of covalent bonds that really influence hydrogen bonding with water. And when we talk about covalent bonds, we talk about electrons being shared, but we talk about electrons being shared unequally. So the atoms develop charges, not full charges like something ionic, but partial charges. Because when you have full charges, electrons are transferred. When you have partial charges, electrons are shared. I should say not shared. Electrons are shifted towards or away. Full charges, electrons are gained or electrons are lost. Partial charges, electrons are shifted towards or electrons are shifted away. When electrons are shifted towards, because you're the more electronegative element, the type of charge you develop is what is known as a partial negative charge, given by the symbol delta minus. In OH, the oxygen has a partial negative charge. In NH, the nitrogen has a partial negative charge. And in C double bond O, the oxygen has a partial negative charge. Where the electrons are shifted away from, those atoms develop what is known as a partial positive charge. In OH, the hydrogen has a partial positive charge. In NH, the hydrogen has a partial positive charge. And in C double bond O, the carbon has a partial positive charge. If you think about water, like alcohols, like even carboxylic acids, water has OH bonds. So the oxygen in water has a partial negative charge, and the hydrogens in water have partial positive charges. Now, the same idea in terms of opposite charges attracting holds true here. If we take water and sort of look at it in combination with any of these other three, where you have opposite charges, they're going to be forces of attraction. Basically, the most soluble type of organic compound are your carboxylic acids. And the reason why is that if you take a look at a carboxylic acid, each carboxylic acid, each single molecule can hydrogen bond with 3 water molecules. Because for a carboxylic acid, not only do you have C double bond O, where we have to consider the oxygen with the partial negative charge as a player in the game, but it also has OH, where that oxygen would have a partial negative charge and the hydrogen would have a partial positive charge. Each oxygen separately is going to be attracted to a hydrogen of water, and the hydrogen of the OH in the carboxylic acid is going to be attracted to the oxygen of another water molecule. And each one of these is what type of force of attraction? Each one of these is an example of hydrogen bonding. The force of attraction between a polarized hydrogen in one molecule and a polarized oxygen in another molecule, in this case. In reality, we don't have to worry about any other portion of the carboxylic acid, because in the rest of the carboxylic acid, you have carbon to carbon and carbon to hydrogen bonds. And one of the key points to remember is that hydrogens on carbon are never involved in hydrogen bonding. Why? Because where OH, NH are polar covalent bonds, CH is a nonpolar covalent bond. And in a nonpolar covalent bond, the atoms are what? The atoms are neutral. So when a carbon to hydrogen bond, the hydrogen has no charge associated with it. It's truly neutral. So hydrogens on carbon are never involved in hydrogen bonding. Okay. A little bit lower on sort of the solubility chain are your alcohols. They form two hydrogen bonds with water per molecule. Let's draw this a little bit differently. So here's our alcohol. OH, oxygen partial negative, hydrogen partial positive. The oxygen of the OH is going to be attracted to a hydrogen of a water molecule. The hydrogen of the OH, man, I didn't draw this other water molecule right at all. Sorry about that. Let's draw it a little bit different. The hydrogen of the OH is going to be attracted to an oxygen of a water molecule. And again, what forces of attraction are you going to have there? You are going to have hydrogen bonding. So their solubility is going to be pretty good. It's not going to be as high as carboxylic acids because carboxylic acids form 3 hydrogen bonds per molecule. Alcohols form 2. But because they form 2, their solubility in water is pretty good. Again, we don't have to worry about the rest of the compound because there would only be carbon to carbon and carbon to hydrogen bonds. And again, hydrogens on carbon are never going to be involved in hydrogen bonding. For your aldehydes and ketones, you have 1 hydrogen bond with water per molecule. And it's all about the C double bond O oxygen. Whether it's an aldehyde where you have at least 1 hydrogen attached to the C double bond O carbon, or whether it's a ketone where you have 2 carbon groups attached to the C double bond O carbon, the key player with hydrogen bonding with water is the C double bond O oxygen. The C double bond O oxygen with its partial negative charge is going to be attracted to a hydrogen of water. And again, that force of attraction would be hydrogen bonding. Even if you have an aldehyde where you have 1 hydrogen, at least 1 hydrogen on the C double bond O carbon, because this hydrogen is on that carbon, that hydrogen would not be involved in hydrogen bonding. And that's a common mistake I see students make. They say that the hydrogen, the aldehyde, the hydrogen on the C double bond O carbon of the aldehyde is involved in hydrogen bonding. It's not. It's attached to carbon. And carbon to hydrogen bonds are neutral. So for an aldehyde or ketone, either one, There's one hydrogen bond with water per molecule. Okay. Then we have amines. Now this is a little bit tricky. Okay. So your your primary and your secondary amines form, let's erase, start. Your primary and secondary amines can hydrogen bond with multiple water molecules. And the reason why that is essentially because of the following. So we'll start with the primary amine on the left-hand side. So you have two NH bonds. The nitrogen, which is common to both, is going to have a partial negative charge. And each of those hydrogens on the nitrogen are going to have partial positive charges. The nitrogen is going to be attracted to a hydrogen of water, and the hydrogens on the nitrogen separately are going to be attracted to oxygen of water. What do you have there? You have hydrogen bonding. In total, how many hydrogen bonds would you have for a primary amine per molecule? You would have 3. For a secondary amine, which we have to the right over here, the nitrogen, there's one NH bond. The nitrogen has a partial negative charge. The hydrogen on the nitrogen has a partial positive charge. The nitrogen is still going to be attracted to a hydrogen of water, and the hydrogen on the nitrogen is still going to be attracted to the oxygen of water. And again, what force of attraction would you have? You would have hydrogen bonding. Here you would have 2 hydrogen bonds that are present. Now, in terms of their solubility and comparing them to carboxylic acids, alcohols, and aldehydes, we're not going to make that type of comparison because we would have to get into more of a discussion about oxygen versus nitrogen itself. So if we're going to look at like soluble, like if you have a carboxylic acid with 3 carbons, an alcohol with 3 carbons, and an aldehyde with 3 carbons, I would expect you to know that the carboxylic acid would be the most soluble, but we're not going to throw an amine into that mix because then we would have to get into more of a discussion of oxygen versus nitrogen. Probably wouldn't ask you to compare amines so much themselves with this one sort of caveat. And that's the fact that tertiary amines, at best, and again, we're talking about 1 to 4 carbons, are slightly soluble in water. Because the biggest difference is what doesn't a tertiary amine have on the nitrogen? It doesn't have a hydrogen. It's possible that the nitrogen, even in the bond to carbon, the nitrogen still might have a partial negative charge, and therefore it might still be attracted to a hydrogen of water by hydrogen bonding. But, I wouldn't say that this is a very strong force in this case. I wouldn't say it's a very predominant force in this case. So at most, I would say that they are slightly soluble in water. But there is a possibility you could make the argument that hydrogen bonding could still exist. So if you had a primary amine with 3 carbons versus a tertiary amine with 3 carbons, which one should show more solubility in water? It should absolutely be the primary amine. So that type of comparison, I would expect you to be able to make. So one of the things you should be able to do with hydrogen bonding with water is to know what types of compounds can hydrogen bond with water and know what portions of them can hydrogen bond with water. Like for a carboxylic acid, it's the carboxyl group, the oxygen and the 2 oxygens and the hydrogen. You should be able to identify those parts and then be able to make some comparisons, like, for example, carboxylic acid, aldehyde, ketone, alcohol, and within the different types of amines as well. So that's sort of the expectations we would have for you in terms of hydrogen bonding with water. In terms of esters and amides, ethers and their hydrogen bonding with water, we don't really talk about them and their solubility in water. So these are the types of compounds to know about in terms of hydrogen bonding and solubility in water. All right. And that was the other thing I wanted to talk about for today. So before we say goodbye, I'll open it up to any last questions you might have. All right. So again, don't forget the exam is on Monday, covering 2 chapters, 12 and 14. Same format essentially as the first exam, part multiple choice, part short answer. A lot of reactions. There's some naming, a lot of naming that was done in the 2 chapters, drawing structures as well. So don't forget about those types of things. A lot of reactions. So make sure you start to work on memorizing them sooner this weekend rather than later. You're very welcome. I will try to have your chapter 14 homework back to you later today or tomorrow morning, and I'll post this recording to Canvas sometime a little bit later on this afternoon. You're very welcome. I hope it helps everybody out a lot. And if you haven't emailed me your time to take the exam on Monday, please make sure you do so sometime before the end of tonight. All right, and that's it. Enjoy the rest of your weekend.